Yeah, the session has been recorded. So yeah, as I was saying, in this chapter, we'll actually introduce to you the procedures. Someone might call them subroutines. So procedures, they they are useful mostly in high level language because of they are reusable. So we write a program such that when we want to perform a certain task, we can reuse that is actually related to that procedure. We can actually use the procedure. Hence, in the test, I was saying those who were passing a certain number, knowing very well that the numbers that are only going to be added is only 5 and are only 5. So if somewhere in the code we asks you that you must actually also input or use the user input to actually insert maybe 3 of your variables or elements in the array, then it means your sum wasn't going to print what is actually required. So yeah, so that's what we'll actually introduce in this chapter. So this chapter is lined up in this manner. So we'll have the stack operation, defining and using procedures, linking to an internal library, and we'll actually go into details. I think in the previous chapters we just only introduced write string and the write int. We will actually introduce more libraries to Ivan 32, and also lastly we will speak about 64-bit assembly program. So if for example you place 10 plates in, or a number can be more than 10 or any other on each other as shown in this diagram here. So the result can be called a stack. That's what a stack is. So if you put a first plate, second plate, third plate until the 10th plate on top of each other, so we call this result what we call a stack. So while it might actually be possible to remove a dish from the middle of the stack, it is much more common to remove the plate from the pot. So a new plate can be added on the top of the stack, not at the bottom. So we from the high level languages, you know, what structure does the stack use? Anyone who still remember? Anyone?
Last in, first out.
So yeah, the last element, or the last object, or the last variable to be inserted, it's what is the last variable to do what, to be removed from the stack, or to be accessed from the stack. So you can't remove the first variable, or the first one that was actually being inserted in the stack. So a stated stack data structures follows the same principle as the stack plate. So new values are added on the top of the stack, and existing values are removed from the top. And stacks in general are useful structures for a variety of programming application. They can be easily implemented using object-oriented method. I don't know if you guys did object-oriented programming. Did you touch a little bit on OOP?
Yes.
Yeah, so yeah, if you did that, uh, you will know that you use what you call data structures. You maybe work with what we call the stacked abstract data type. So, like we said, the stack uses the LIFO structure because the last value uh, put into the stack always is the first value to be taken out. So always remember this. So we have what we call the runtime stack. So the runtime stack, this is it's a memory array managed directly by the CPU using what you call the ESP. Still remember what we said in the test when I asked what is the ESP, what is its function? Do you still remember? We said it's a what?
Step point.
Yeah. So the runtime stack memory array is managed directly in the CPU using the extended stack pointer register. So the ESP, which is the extended stack pointer register, also known as a stack pointer register. So in Ivan 32 or in 32-bit mode, ESP register holds the 32-bit offsets into some location of the stack. So um, we really manipulate the ESP directly. Instead, it is indirectly modified by instructions such as call. You'll see them when we go, such as you'll see them the call instruction, um, the read instruction, the push, and the pop. I hope you guys did your assignment well last week when I was asking the question about the push and the pop. So always what you must know is that the ESP points to the last value that was added or which was pushed to the top of the stack. It follows the very same structure that a high level programming language or OOP programming languages follow. So the ESP always it always it points to the last value that was added to the stack. So, or maybe the value that was pushed on the stack. So to demonstrate this, let's begin with this example on this figure, right? The ESP contains an hexadecimal offset of 0001000. So the offsets of the most memory pushed value, which is 006, which is 6 decimal or 6 hexadecimal. So you can see from this diagram. So a 32 pushed operation decrements the stack pointer. So by what? By 4 and copies a value into the location pointer to the stack point. Why does it decrement it by 4? Why does it decrement it by 4?
Using the sense of 32-bit is 4.
Are we cheaper now? They have cheaper. Yes, ma'am.
32 bits consists of 4 bytes.
32 bits consist of 4 bytes. So, yeah. So that's why it decrements. So if it was 16 bits, it was going to decrement by what?
2.
By 2. Thank you very much, ma'am. Nice one. Anyone? Mohamedin Guji. Mohamedin Guji. Mohamedin Gurji. Yes.
Hello, sir.
Yes. How are you, my friend?
Good, thanks, and you?
Mm.
Sir, so we decrement since we are pushing.
Yes, but they say, okay,
Because
this was happened. So the push operation, right?
yeah,
The push operation so it decrements the stack pointer by 4 and copies the value into the location in the stack pointed by the stack point, right? So you can see in this figure, which shows that after another value was pushed, right? Or which is we can say it's 000 a5, right? So the 00 a5, when it was pushed on the stack, that already was containing 0 what 006, right? So what you must notice is that the ESP register always points to the last item pushed in the stack. Initially it was pointing to what, Mr. Gurji?
it was pointing to 00006.
Yeah, before it was pointed the ESP. I'm happy that you can show. So the ESP it was pointing to 0006, right? Isn't it so?
Yes.
Yes. So after that, when we pushed 0000A5, 6 zeros and A5, so the stack pointer, it has to be decremented by 4 since it's 16-bit, right? So when it's decremented by 4, you know it's going to ask for carries from 1, and then you know it will leave 15 there, 15 there. Okay, it will ask base 16, and then we ask from that base 16, we minus 1, then it will be 15, and then again we ask another base 16 again, then we will have 15 again, which is FF, and then 15 minus 4, it's what?
15 minus 4 is
I mean
11.
16 minus 4, it's 12, and
It's
12
12.
it's C. Yes, you see. So yeah, I don't know if you get it. So what was your question exactly, Mr.
Oh, I
Gurji?
just wondered, since we are pushing from the top, so I wanted to know, like, why we decrement, because isn't it the bit it counts from bottom to up?
The what?
Since isn't here we are gonna be counting
So the
FF0,
most important part
FF4,
is
FF8, like that. So that's the reason we decrement.
so the most important part is here, right, Mr. Gucci? The most important part is here. The
But
ESP,
I
right?
do understand now.
Okay.
Yeah.
I don't know if what is it that you are understanding, Mr. Mohammed? So that hey, Mr. Mohammed.
I understand, sir.
Okay, no problem. So yeah, you can see that from this figure we have, like as I was explaining to Mr. Gushi, that so not Gurji, that the initially the offsets of the ESP was in the memory was 0004000, yeah, 1030 zeros after one, right? Which had a value of 0006 in the stack. So we added another A5, which actually was decremented to FFFC. You know what? Where we got sorry, you know where we got this decrement. So if you minus, for those maybe who are shy to ask, so if you say 1, this is 1, is it 100 or 110? Okay, 1000. So 100, this is in H, and you decrement it by minus 4. Okay, let's do this. Minus 4. And then 1, 2, 3, 4. So obviously 4 will come here and it will find that this is 0. So it will go and say, go and ask for something in here. This guy will say, no, I don't have anything. And then this guy goes and asks something in here and say, no, I don't have anything. And they will ask here. And then things starts here. So when things starts here, so we are going to do what? We are going to ask for the base, which is what?
16.
Which is 16. When we are asking for base 16, then here we are left with what? Because we must minus how eh?
15, which is F.
Are you sure? We are left with 0, mister, because you are going to minus 1 from here. So when we are asking for 1 here, it comes as a base here, but here on the actual number we have to minus 1. So 1 minus 1 is 0. So here we'll be having base 16. Then we'll ask for again this here. Here we will know that, okay, since it's 16 here on 0, then it means we must ask for again base 16, and then here we'll be left with 15, and then 16 will come here, and then we'll ask again, and then here we'll be left with 15, and then here we'll be left with 16, and then 16 minus this 4. Now the subtraction it's okay, or the decrement can decrement now. So we'll be left with 16 minus 4. 16 minus 4 is 12. And 12 in hexadecimal, it's what? It's C. And remember that on here we're left with 15, and it means it's F. So hence we have, hence we have this. I don't know if FFC. So that's why when we decrement, the offset ends up like that. Do you get it, or you want to forget about it for now? So if if after that you again push on the stack 2 more integers, example 0, 0, 0, 0, 0, 0, 1, 1 and 2. So it will decrement from C. It means it's going to be C minus 4. C minus 4 is 12, minus 4 is 8. And then 8 minus 4 will be 4. And then, yeah. So hence you see now the ESP is pointing to the last added value, which is 0, 0, 0, 0, 2. So can we pass? Any question? Any question? No question. Mr. Mreto Guji Komani class Mama Bolo Presella Chavala.
I have no questions, sir.
Okay. Mr. K.
Oh, say, is the right runtime stack growing downwards in memory?
Growing what?
Downwards, growing downwards in the memory since we are moving from higher addresses to lower addresses.
So, but my question is, Mr. K. Hey, Mr. K.
What is your question?
What is the question?
My question is the right runtime going downwards in memory?
It decrements.
Okay.
Yes. Thank you, Mr. K. Thank you, Mr. K. Are you fine? So we have what we call the pop operation. So the pop operation now, this one removes a value from the stack, right? You know, even in high level, you have something like that, which we can remove a value from a stack. After a value is popped from the stack pointer increment. Isn't it so? You can see from this figure that initially we had 006, 0000A5, 001, 00. Then we popped. So remember, we are going to pop. It means we are remove something from the stack, and then the stack uses the LIFO structure. Is it a last in, first out? The LIFO structure. So when the ESP now is pointing to the last added value in the stack. So if you say pop that, then it will remove 000002, and then now after the pop, the ESP has to point to the value that was added before 002. Now the ESP is pointing to 8701. So I don't think that is too much of rocket science, isn't it so?
Yes.
So the area of the stack, if you can see the area of the stack below the ESP, this areas, right? The areas on the stack below this ESP, even from the previous slide, right? Is logically empty and will be overwritten the next time when the current program execute instruction that pushes a value on the stack. So we have various applications. There are several important use of runtime stack in the program. Anyone who can provide me with those fast so that we can move to push and pop instruction. Anyone? Anyone? I'm saying the question is, what are several, or anyone can name several uses of runtime stack or in programs? Yes. Put your hand. Lord. Tobela.
Yes, sir.
How are you, Ma'am Lodi?
I'm good, thank you. How are you?
I'm good.
So a stack, it provides a storage for registers when they are used for more than one purposes. For more than one purpose.
And then does what? So you're saying it provides what? The temporary storage for? Or what?
Registers. It provides a temporary storage for registers when they are used for more than one purpose.
And then again?
It provides temporary storage for local variables inside subroutine.
So what happens when you are calling those subroutines?
When you're calling them, you need to pass down inputs by pushing them into the stack.
Which inputs? And what are the names of, what are they called, those inputs?
They are called arguments.
Oh, okay. That's nice. So yeah, so you are explaining it. So when there are several important uses of this runtime stacks, wherein as Mem has explained, that a stack can makes it a convenient temporary safe area for registers when they are used for more than a single purpose. And the one Mem said again, when you are calling subroutines, you can pass input values called arguments by passing them to the stack, and also the stack can actually provide the storage for local variable inside the subroutines. So yeah, thank you very much, Melody. So we have the pop instruction or operation. So the push and the pop. So the push instruction, first, what is that? The first thing that it does, it decrement the ESP and copies and then copies a source operand into the stack. So the first thing that it does, you must note this thing down. It decrements the ESP, and then after that, the operands that are copied to the source. I mean, there are source operands that are copied to the stack. So as I don't know who said, is it Mem who said in 16-bit operand they causes the ESP to actually decrement by 2. That's actually what we actually got from the beginning when we're speaking about the push and pop. So this is this has 3 variants. The first variant is you can push from a register or from a memory in 16-bit, from a register to memory in 16-bit, or push an immediate value in 32 bit. And also the pop instruction, what it does first, it copies the contents of the stack element pointed to the ESP into a 16-bit or 32 destination operand, and then increments the ESP. So this one, it doesn't agree now. What the difference now? What, so from this, anyone who can actually spot the difference from the push and the pop? Anyone? Yes. Joyful.
The push instruction decrements then copies. Then the pop instruction copies then increments.
Yes, that is the difference between these two. So the other one pushes and then copies, and the other one copies then. I mean, so the other one copies and then increments, and the other one decrements then copies after. So yeah, so when we decrement, we copy after. When we increment, we copy first. So that's all in all. So save and restore registers when they contain important values. Push and pop instructions occur in opposite order, so you can see from this code. So I'm gonna give you 5 minutes to actually just write a simple code apart from this one that you can actually mimic push or pop. 5 minutes, guys. You have only 5 minutes. And I'm gonna expect different hands from the ones in the presenters. Yeah, anyone? Morning. Morning. Anyone? Mohammed?
Yes, sir.
What do you have for us, Mohammed?
Yeah, I think I have something.
Yes, mister.
You move this is the simplest one. It doesn't have ESI or ECX or EBX. But let me just try. You move 5 into AX. That's the first one. And then you push AX into the stack. Then after you're done, you pop BX, meaning whatever that was in AX will be popped into BX. Then the code is done.
You move what?
Firstly, you move into AX. Then you're going to push AX. Then you pop BX.
Mm. So yeah, I was a little bit distracted. So let's do this, ne? Let's open our Visual Studio to actually do this. Where it's our VS Code. So let's do this in writing. So I don't know if I should delete this one, but let me not delete and come open folder. And then come to use it, come to score and add the folder. Okay, let me just say chapter 5. And create. No, this is not going to be good. Let me do this. Yeah, let me add folder here and say chapter 5. And then come here. So what can we name our Muslim code? What should we name? Push and pop. So it will be push or pop or ASM. Obviously, we must all start by saying, including, we must call all the libraries from Ivan 32. And then from there in the data section, we can actually initialize. Let me just say .data, and then in the code section, and then what's it been? Then we can call this our main main proc, isn't it? So, and then we can have a part where we are going to exit, and have the last part where we can actually end the main proc. And the last one is what? Anyone? Number guys, go with me.
And main.
So in here we can initialize what? Let's initialize two the word values. Let's just work with two, and let's say it's val1, right? Or var1, or whatever that you can name is still okay, and call it the d word of that value, and it's a 10h, and then value what? Value 2, and then we call it of d weight, I mean, and let's just give it 20, and the last one we can just have the result from this results, which are d weight. And what should you make our result? 0 or null, or they should accept input at runtime?
Accept.
Huh? We should make it to accept the input. So firstly, we can start by loading the what? Loading the value. This is the first thing that you can do. Load. This is not load. Load those values into registers. Let's say EAX and EBX, and then you can just have your move EX var1. Then now we know that EX now it's how much?
10h.
10h, isn't it so? And then from there you move EBX. So when I'm making errors, you guys can actually come forward and make sure that I correct that. And then from there, so that was moved to EBX. Then EBX, we know it's equals to what? But most of the things you guys will do them in practicals. And then from there, now let's push values. Is it it is not value. Let's push values into onto a stack, onto the stack, right? And then from there you can say push, right? EAX, like I said there, right? Then we know we pushed we pushed EAX, right? That is what 10H, isn't it so? And then from there you can say push EBX. Let's not dwell on that example. Okay, this is push. They are not case sensitive, I got of it. So don't worry about me writing them in. And then we pushed EBX 20. And then now you can actually pop values back, right? So into the LIFO order. So let's just say, now let's apply pop values back, right? So you can just say pop what am I writing? Pop EC. So why do we say pop ECX? Hello?
Yeah, so it's a destination operand.
Yes, this is the destination operand. Thank you very much. So this thing, it means you are popping which value?
Value 2.
Which value are we popping? Anyone to assist us, Captain?
NDH, the last one
The
was
last one.
entered.
Yeah, thank you very much. So we popped this. So it means whatever that we are popping, it must be placed into what? It must be placed into what?
ECX.
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 So now so ECX is equals to 20, right? And then this was popped from what? Which was popped from EBX, right? And then you can just say pop what? EDX, right? And then which EDX will be equals to what? Anyone? 10H, right? Which was popped from what? EAX, isn't it so? And then from there, so you can actually add what? Add the popped values. Let's just add them and place them at ECX, EDX, and you know this is ECX, will be equals to 18, 20, and 10, 28. But you will know that these are 28s, né? So that we don't spend too much time here. And then from there, and then you can move whatever that is written here to results, isn't it so? And there, which is ECX. Therefore, lastly, you can actually call let's just call the dump registers and here. So before we can run the code, or before the code gives us errors, do we actually understand? Hello guys. Hi. Do we get it? Or we are likely to forget? Huh?
Yes, we get it.
So what happens is that the push, it saves agar. It saves registers values into the stack memory, isn't it so? And then the pop what is going to do is going to put them in reverse order. So obviously when you're pushing them, they will save to where? Hello. So now let's save the code. Hope it's saved. Save. And then take chapter 5 and bring it here. Let's try to run these errors. It assembled, and that's what we get from it. So initially EAX was containing 10H, which is 10H. You can see it from here. And then you can see EBX was containing 20H. And then we popped EDX. Lastly, the last one which was popped was 10. It was moved to EBX. And remember in the ECX, it was the destination here where we put everything, where we added everything into it. So can you see an example of how these things work? Hey guys.
Yes, sir.
Yes. So yeah. So you can, when you're creating a nested loop, push at the outer loop counter before enter. You can see from there, if you still remember you see this is L1 is it the inner or the outer loop?
Outer.
Yes, this is the outer. So the first thing you must do is you have to push the outer loop counter before entering into the inner loop. So you can see from here we push the ECX, which saves the outer loop count, and then from there we can see we moved to the ECX20. So it means here when you say ECX is 100, we are trying to, if it was a array of even, it means you are trying to transverse through it 100 times, and here it would be 20 times. So yeah. So example of reversing a string. So you can actually use a loop with indexed addressing and push each character on the stack and start on the beginning of the string, pop the stack in reverse order, and then insert each character back into the string. So yeah, you can find the source code there. And then why must each character be put in EAX before it is pushed? Anyone? Anyone? Common.
Oh, that one is a source operand. So we need to copy things from the source operand into the stack. So I don't know if whether we can copy like other variables which don't contain registers.
Another, I had a hint. Surprise, Mr. Mlotro and Mudau, my lady.
Sir,
Mm,
I think it is
mm,
because we want to reserve a space for it since we don't know how much space it is gonna need.
mm, mhm. So let's do this. So can we do that example together before I give you a turn to use a string to reverse a program as a starting point? Can we do that together? Or should we move forward with the lecture? Hello, guys. Should we do it together or should
Let's do it together.
okay, let's do it together. So this would be what can we call our file here? So we want to write a string, right? And actually reverse that string into that. Ne? So what's going to happen is that here we'll have an example which reverses a string. So the file can be named, let's just say reverse string, and then you can come. Oh yes, what did I do? Just call it rs, and then that rs we put your file and then say rs reverse string dot asm, and then we come here, and then we have to include i132 dot inc, and then from there in our data, which string can we name or can we actually declare? So let's declare my string as okay, let me come here and try to say control a copy and control what's gonna happen, and let me remove everything in here so that we don't actually write things from scratch. So I was asking which string can we actually say? Let's just call something my string, and then we take it to byte and we name that string hello and make it. So this you know that it would be the original string, which is null terminated string. And then from there you can say reversed byte, say size of. So from here, what will the size of do? Here, guys.
My string.
It will do what?
It will take the size of that string with bytes 111.
So what are we actually trying to do now here? Anyone? Anyone? Or shall we pass? So we are trying to store, right, a reversed string, right? So we are trying to store a reversed string. So I don't think that we have to. What is it that we can initialize? So you can come here and say, let's try to first thing, try to actually get the offset of my string, right? So we are going to move ESI, right? I don't know if I return it nicely. ESI, and then we say offset when I'm doing errors. You guys must actually tell me my string, right?
Offset.
Or it's offset. So yeah, it's okay. So here we are saying, now let's do what? After doing that, the first thing that we can do is to do what? You can have a loop, right? You can have a loop, and then we say here we are pushing each character of the string on the stack, right? Or onto. So what's the real onto or on the? So we'll have the push loop. We can name it the push loop, right? And then in the push loop, this is what we're coming. In the push loop, this is what you expect to do. Since we have initialized our thing to byte, which register are we going to work with?
AL.
So the AL, so you're going to move AL what? And then what should we do here? Anyone? This is some of the things here from the test. Anyone?
It's going to be ESI with the brackets.
So we have to dereference ESI.
Yes.
The references of those EAI. Right? And then you will have this thing, some of the things you'll see them as we move on, because yeah, they are in the chapter. So when we want to end this string, right, we have to use what you call the command called the CMP command, CMP or CMP, right? Then you CMP AL such that AL is 0. So this guy here, unfortunately, I don't think we will end the session today because I'm busy coding here, but it's fine. The end of a string. So after that, right? This is so is this the end of the CMPL? It will ask end of the string. If is it not the string? If yes, then start popping. Then now there's another condition which is called the JA, the JIN, where you have to pop the loop, pop loop. Let's call the pop loop. So should we name? We have never initialized. So what should we? Okay, let's initialize this first. Let's now start by incrementing ESI. ESI, and therefore you know the JM. What does the JM means? The instruction do? Huh? Guys,
Jump.
it does what?
It jumps
Okay, to what? So it's going to jump to what?
it repeats the loop.
Okay, it's fine. So here, let's try to do this. Let's try to pop characters, right? Let's try to pop characters now. Pop characters, just to reverse order. Reverse order. So we can have what we call the pop loop. Let's have the pop loop. Pop loop, and in the pop loop we move the offset to ESP, move E. No, we can't move them to ESP. Let's move them to EDI.
So,
Yes.
do we move or pop?
No, now agree this is the pop loop, right?
Eh,
Yes. So now in the pop loop, let's move this offset. I can remember when we pop it means we are doing what? We are removing, right? So
yes.
we'll pop. We'll have another loop which will pop the next, and another last one which will be the one that actually terminates the reverse string if the string is done. So let's move. So when we have the pop loop, right? Let's move the E. I don't know if the register it's EDI, right? And then the offsets of the offset of my string. Let's take my string. So here, what we are trying to start to EDI now. Oh, sorry. EDI, right? Is going to do what? It's going to points to this testing. It's going to point to this. Let's just say this, and a destination will be this string.
So
yes, Mike.
don't we use the reversed one?
We must use the what?
Instead of my string.
Yeah, it should be the. Thank you very much. Thank you very much. I appreciate that, Mr. Gucci. I appreciate that. Ne? Guji.
Yes, sir. Thank you.
So now we are going to check if we have to use the condition if that thing is the start of the string. If it's yes, then start popping, right? So it means if we are going to have the condition here, which is going to be the J condition, we are going to do it on the pop loop such that if yes, then if yes, then what? Start. You must start popping, something like that. So we move, isn't it so? Then from there we can push. Now we can push. We can be able to push because we didn't push here. We can push the we can push EAX, right? Okay. So what does this thing do? What does when we push this thing, right? This will push the characters, right? Only the AL remember its use, which is the upper bits will be ignored. Then from there we increment the ESI, right? This will push the char, and I said only the upper bits will be only, okay, the upper bits will be ignored, and then from there we increment the ECI and also jump to the push loop. And then from there, after we are done with this loop, we will actually have a loop which we can call it pop n loop. Okay, pop n. So this loop will pop next, correct? So you can just call it pop n or pop. Okay, let me just say next, so that when you start you don't remember, you don't. So you can use, you're gonna use another CMP so that it stop when the stack reaches the start, right? So when the stack reaches the start, which is the value that was actually pushed first, right? Then this thing must stop. So you're just going to say CMP ESP. ESP is the what? Is the stack point, and then you say offset my offset of, we are going to check to take the offset of my string or of the reversed. So this is going to be the offset of the, I mean, not reversed, yeah, of the reverse. This one actually, what does it does? It I said it okay, it stop when the stack reaches start, and then from there what do you do from there? Are we lost?
Yeah, and I'm lost, sir.
So okay, this one, the first loop here, we are trying to push. We want in this manner, if we want to push this thing in the hello in reverse order, right? We will have the first loop which pushes each characters of the string into the stack, right? Which is this guy. And then after that loop, we'll have the loop that has to put characters in reverse order, or loops that actually pop characters in reverse order. That's what's going to happen. And lastly, we have to actually print the string. So yeah. So that I will give you the question.
So, say we don't need the loop counter to control our
What's
loop in
going
this
on?
case.
What's going on here?
Say, am I audible?
Yes, you are audible.
Yeah, I was asking. So we don't need the loop counter to control our loop in this case.
The what?
The loop counter.
The ECX.
Yeah.
To what? To
To
control
control
our?
our loop.
No, here we are going to be using the conditions. That's why we are using the JE, which has conditions. It's going to only check if the loop it's empty or not empty. If it's not, then it must always pop.
Okay, sir.
So, but let me not overload you with information, unless if you want me to continue. But I will give you this as a question, and then, but at the end, whatever that you'll be doing, it must take hello.
So we can no
If
longer see your screen. We can't see your
you
screen.
cannot, you can't see my screen.
Yeah.
Okay. So what I'm gonna give you this as a question, right? But let's, for the purpose of finishing, let's finish, and then yeah, it's gonna convert hello into ole, if I'm not mistaken. It's going to be ole. If that's yeah, ole. So I'll actually bring you that question to your attention. So yeah, so that's it. So again, in that program that you do, you can actually write two of them. I'll give you the two questions, where in the question you can actually modify the string, and also modify the programs that it can input at least a list of 32-bit integers from the user, and then display the integers in reverse. So yeah, so related instruction to push and what we call to push and pop. We have what you call the pop df. What does the pop df does? Is it pop, not pop df? I mean the push fd does, and the pop fd does. Yes, yes. Mudau, Mudau.
So I think the push FD is going to save the flags on the stack, and the pop FD is going to restore the flags on the stack. From the stack, I mean.
It does what? The push fd does what?
The push FD is going to save the flags on stack, and the pop is going to restore the flags from stack.
Yeah, so what's happening is that, yes, what's happening is that the push fd pushes the D2 bit. So you must you must actually have this in your mind, that the push FD pushes the 32-bit flex register on the stack, and the pop FD pops the stack into the E flex, into and onto the stack. So pushes the 32-bit E flex, which is the push FD, pushes the 32-bit E flex registers on the stack, and the pop FD pops the stack into E flex. Again, we have what you call the what? Push AD, and the pop AD, the pusher and the popper. So the push AD instruction, this one, it pushes all the 32-bit general purpose registers on the stack in the following order: EAX, ECX, EDX, EBX, ESP, EBP, ESI, EDI. And then the pop AD instruction pops, or the pop, what we call popped or popped instruction pops the same instruction, or pops the same registers, which is the EAX, ECX, EDX, EBX, ESP, EBP, ESI, and EDI of the stack in reverse order. Similarly, the pusher instruction pushes the 16-bit general purpose registers. The pusher and the popper do the same thing as the popped, but in 16 bits. So my question would be, what will the pusher instruction push, or which 16-bit general purpose registers will be pushed if you say pusher? Anyone? Hello?
So can you repeat the question?
I'm saying, what will the pusher, this one, instruction, the pusher, I will say the pusher, right? It pushes the same registers, right? But in 16 bits. So I'm saying, which registers will be pushed when you say push in 16?
AX, CX, DX, and so on and so on.
And what? It can be so on and so on.
Oh, AX, CX, DX, BX, SP, BP, SI, DI.
Yeah, SI, BP, DI. Yeah, something like that. So yeah. So the other one, it will reverse them in order. So now, yeah, 10 is to actually go and write. So you have the question. The question that you'll have is that you're going to write a program that actually output a string in reverse order, and lastly have manipulate that string so that it can take 50 characters, and also that. So another one that you're going to write the program does that does the following: assign integer values to this, and uses pusher to push the general purpose registers, and also use the loop. Using a loop, your program should pop each integer from the stack and display it on the screen. So yeah, that will be another question for the day. So now we will be dealing with what you call creating and defining procedures. So we know that large programs can be divided into smaller tasks to make them more manageable. So you learn that from C++, such that when you have a large program that actually has many functions within it, you need to actually divide it into small manageable task. And why are we doing that? Why are we doing that? Why are we doing that?
So that our program can be easily read. No
So that our
complication.
program can be what?
I agree we will know that this function deals with specifically with this part, and the other procedure deals with the other part. So you'll know what to do. Yeah.
Okay. So there is a suggestion here.
Yeah, we support it.
Why?
Too much information.
Too much information. Oh, you guys were stressed by the code, Mohammed. And we are not
Yeah.
done with writing this code. This code is we are still left with how many loops?
Yeah, we are still not done.
1, 2, 3. So we should have the loop that we are going to give it. Yeah, that we are going to give it instruction of checking if the thing is done popping out those things from. And then yeah, I think we do pop next. Yeah, we did pop next. So we were left with only one loop to actually finish this code. So yeah, so if you are saying so, we'll have a class on Friday. I was saying I'm going to give you a quiz, then we'll have a class on Friday so that we can wrap up. So once we are done with creating procedures from here, going down there, we don't have too much theory. I mean, too much practical. It's just theory, and most of the things you know them. So I'll create an online link so that we can join on Friday, isn't it so? Hello.
So please repeat what you just said.
I'm saying from procedures, after we're done with procedures and after we're done with creating procedures, we are no longer anything that is more practical. What will be left from now is it's theory. Most of the things here, they are just theoretical. So hence I'm saying we'll have a class on Friday, wherein in the class we'll try to actually finish or wrap up with this chapter such that next week Friday, the date that we agreed on with the quiz, you guys can write a quiz, right? On the 5th of September. And then next week, Tuesday, we'll start with chapter 6. And then we'll finish it on the following week, Monday, Tuesday. And then we'll start with chapter 7 on the 12th of September, such that. When are we closing?
But sir,
Mm.
isn't you said that we'll do only 2 chapters, chapter 5
No,
and
in the
6?
test, you'll only in the test, ne?